So let's take a look at the periodic table. It was first organized, or Dmitry Mendeleev is given the credit for sort of discovering how elements are organized, or putting them in an order. So, of course, at the time, he didn't know about an atomic number. He arranged them in order of mass. But if you take the elements and you arrange them in order of atomic number, they're placed in horizontal rows in a way that the elements that are in a vertical column have similar properties. And so this is called the periodic table because we have a repeating pattern that comes, so like periods. They start and finish and start anew, a regular repetition. Okay, so if we look at a modern periodic table, we can see that there are periods that go across. One, period two, period three, etc., down to 7. We also have groups or families that are columns of up and down columns of elements. So we have our main group elements. Notice the numbering. So there's two types of numbering systems. You can either look at the A and B system, which are sort of Roman numerals. So there's 1A, 2A, and then 3B, 4B, 5B, 6B, 7B, 8B, 1B, 2B. And then we jump back to the A's, 3A, 4A. That's one set of numbering where the A's and the B's are separate. So the A's are called the main group elements and the B's are called the transition metals. The newer numbering system goes 1 through 18, which doesn't distinguish between the two. I kind of like the older method with the A's and the B's because we're mainly going to focus on the A elements in general chemistry, although we'll look at some of the transition metals, but our main focus will be on the main group elements, the A's. And then you can also see down at the bottom there are some transition metals, which is a third group, the intertransition metals. Those are the two. And actually, if you look, you can see that the periodic table kind of opens up and they stick in between after 57 and between 57 and 72. That row goes in, and then another row between 89 and 103. Also notice that this periodic table, they're split into metals, nonmetals, and metalloids, which we'll talk about in just a minute. So you can see that there's a sort of a zigzag line starting at the top of column 13 under boron, and that zigzag line, dark line, goes all the way to astenine, which is number 85. And so you can see that the metals are all to the left of that line, and the nonmetals are to the right of that line. The orange squares are the nonmetals, and the blue squares are the metals. And then right on the edge, if you want to go strictly speaking, everything to the left of that is a nonmetal, everything to the left is a metal, everything to the right is a nonmetal, but those green squares that lie right on the border are called metalloids, and we'll talk about those properties in just a minute. All right, so this is kind of what I've already said. A period is going across in a horizontal row. A group consists of the elements in any one column. The groups are numbered, and like I said, there's 8 A groups, which are called the main group elements or representative elements, and then the B groups are called the transition elements or transition metals, because they're all metals, and then the 2 rows at the bottom of the table are called the intertransition elements or intertransition metals. The column 1A, some of the elements have names, and so like I just said a minute ago, elements in any one group have similar properties to each other. All of the elements in group 1A are called the alkali metals. They're all soft metals. They're all very reactive. They don't exist very well as a metal. They're mostly react as or exist as ions. The elements in group 8A on the very far right hand side are called the noble gases. They generally don't interact or react with other elements, and so that's why they're called noble. Group 7A, so one just before the noble gas, are called the halogens. They're also very reactive elements, but they all tend to be gases or liquids at room temperature, although it changes from gas to liquid to solid near the bottom. Iodine is a solid. Group 2A elements are called the alkaline earth metals. They're not quite as reactive as those in Group 1A, but they are fairly reactive. Okay, so I mentioned earlier that you can also look at the periodic table and tell where the metals, nonmetals, and metalloids are. We looked at that zigzag line as the dividing point. So what are some of the characteristics of these types of elements? So metals generally, and you probably know this already, metals generally are shiny or lustrous, have luster. They are good conductors of heat or electricity They're ductile, which means they can be drawn into thin wires, and they're malleable, which means they can be flattened into sheets. So a nonmetal then is something that does not exhibit the characteristics of a metal. So what does that mean? That means they tend not to be shiny. They are not good conductors of heat or electricity. If they're either, nonmetals tend to be gases or liquids, mostly gases. A few nonmetals are solids as well, but if they are, they tend to be brittle, not very hard. If they are hard, they're brittle, they break easily, or they're kind of soft and not very they're not going to be like a wire or a flat sheet. They're not very good at that. So a nonmetal is the opposite of a metal. And then in between we have a metalloid, which can also be considered a semi-metal, partly metal, and it has both metallic and non-metallic properties. And a couple of interesting metalloids. You've probably heard the term semiconductor. So they're not great conductors, but they're not bad conductors either. Semiconductor are used a lot in computers. Silicon and germanium are two of those kind of metalloids that are used in that industry. All right, so chemical formulas and molecular and ionic substances. So it's kind of hard at the beginning here because we kind of need to learn a lot, but you just kind of learn it a little bit of a lot of things to get us started so that we can talk about chemistry, and then as we go through the year we'll learn a little bit more of each of these things. But anyway, when we have a compound, molecule, or any kind of compound, we can write it with a chemical formula. So the chemical formula is just a notation using the atomic symbols from the periodic table and then the subscripts telling us how many of each element we have. So if you look at something like Al2O3, what does that mean? That means that my compound in question has 2 aluminums and 3 oxygen all bound together. No matter where you get it from, they'll also have this 2:3 ratio of aluminum to oxygen. So Al2O3 would be considered a chemical formula. A molecule is a group of atoms that are chemically bonded together, which means that they're connected by very strong attractive forces. So a molecular substance is a substance composed of molecules. There we go, all of which are alike. Then the molecular formula will give the exact number of each type of element. So that's sort of similar to what we saw earlier. Now we can then take the molecular structure a little bit further and look at structural formulas, which we'll do actually at the end of the first semester. So a structural formula actually shows how they're attached to each other. So this is just a little bit of the survey. So you can see the molecular formula just shows the ratios of the different elements, and then the structural formula shows how they're bonded together. And then we also have a molecular model, which again, by the end of the first semester, we'll be playing around with some ball and stick models. And then the molecular model, space filling, tells you even a little bit more about the structure of the molecule. All right, so there's actually two kinds of substances. There's ionic substances and covalent substances. And so, again, this chapter is just a little bit of a mishmash of all kinds of things. So what is an ion? Have extra electrons or have some electrons taken away. So an atom or a group of atoms will have added electrons or removed electrons to make an ion. So it's an electrically charged particle. So if an atom picks up extra electrons, it becomes negatively charged, and we call that an anion. So chlorine, for example, will gain an electron to become Cl negative. It's very important that if you're discussing ions that you put the charge, because a Cl by itself means the element. A Cl negative means that it's gained an electron, and it has very, very different properties if it's a negatively charged ion. An atom that loses electrons will become positively charged, and that is called a cation. I always remember which is which because anion is, you can think of it as a negative ion, anion, and then cation has the T in it, which sort of looks like a plus sign. So you can remember that the cation is the positive ion. I always have a joke that I like to tell. Maybe you can remember this. It's not a very hard concept, but students especially have a hard time with the fact that when you lose electrons, you become positive, because you're thinking, well, if you lose it, you're losing it. But remember that you're losing something negative. So if two atoms are walking down the street and the first atom says to the second, "Oh no, I lost my electron," and the second element said, "Are you sure?" and the first one said, "Yes, I'm positive." So again, if you lose your electrons, you become positive. So Na loses one electron to become Na plus. Okay, so the simplest kind of ion is called a monoatomic ion, which is formed from a single atom. So when Cl gains an electron, becomes Cl negative, that's a monoatomic ion. Mg will lose 2 electrons, become Mg2 plus. O will gain 2 electrons, become O negative 2. We can also have a group of atoms that as a group either gain or lose electrons. These are called polyatomic ions. So you can see some examples. NH4 together lose 1 electron to become NH4 plus. SO4 together gain 2 electrons to make SO4 negative 2. The sulfate ion, and ClO4 gains an electron to become the perchlorate ion. I highly recommend learning all the polyatomic ions that are found in table 2.6 in your book, page 54. And you want to recognize them. So with their name, their formula, and their charge, they show up in so many compounds, and it can get very confusing if you're not able to identify them or recognize when there's a polyatomic ion, especially right here at the beginning. So actually here is the table that I was talking about, and you'll notice that I have starred some of them. So like I said, I highly recommend that you learn the polyatomics, at least the starred ones, because they show up a lot. So the ammonium, the carbonate, acetate, the perchlorate, the chromate, dichromate, permanganate, nitrate, hydroxide, phosphate, and sulfate. Those show up a lot. The others and if you want to print off this table and keep it with you at least for a while to recognize the polyatomics, when we get into naming compounds or forming compounds using ions, it's very handy to be able to recognize a polyatomic ion, especially when you need to break up compounds. So again, you might want to print this and have it handy so that you can recognize them. All right, so I Ionic compound is a compound composed of cations and anions that are attracted to each other because they have opposite charges. So Na plus and Cl negative come together to form NaCl, which is an ionic compound. The formula then, NaCl, is always written, the formula of any ionic compound is written in order to give the smallest possible whole number ratio of the two ions. And they have to come together in such a way that the charges cancel each other out, because the compound itself is going to have to be neutral. So in this case, Na and Cl, Na is a +1, Cl is a -1, and so they'll form a 1-to-1 ratio, so NaCl is the formula. So actually, an ionic formula only gives, like I just said, gives you the lowest ratio. So for Na and Cl, it's a 1-to-1 ratio. But what happens when they do come together, since Na plus is going to be attracted by all the negative ions, they're going to surround it. And all the negative ions are going to be surrounded by positive Na plus ions. And so actually what you end up with is kind of it's called a lattice or crystal structure, where you've got a Cl surrounded by Na plus, and you've got an Na plus surrounded by Cl negative. But again, the ratio in this case is 1-to-1, 1 Na and 1 Cl, and so the formula is just the smallest ratio that you can have. All right, now, ionic compounds are electrically neutral. So I just mentioned that a minute ago, but this is critical. An ionic compound, when they form together, they always have to go in they have to pair up in such a way to make the compound neutral. So the positive and negative and fluoride want to come together to form a compound. Well, the calcium is a +2 and the F is a -1. So if they come together 1-to-1, they're not going to be neutral. It'll overall be a +1 charge, because a +2 and a -1. So that cannot happen. So the best thing we can do, we need to have a +2 total charge, and we need to have a -2 total charge to balance each other out, the lowest ratio. So the only way that we can have a -2 charge from the fluorines is to have two of them. So if we have two fluorines, they will each give a -1 for a total of -2, and so the charges will be balanced. So the ionic formula then is CaF2, because we need two fluorines to balance with every calcium in order to have a neutral compound. All right, so let's kind of do a few more examples. This is probably a huge thing that you should be able to understand, because it will stay with you the rest of the semester. So if you don't get it now, you're going to struggle with a lot of other chemistry. So let's look at some other examples. Kind of what we're doing is looking for a least common multiple. So you can see in the first example, Na and Cl are both 1, so the least common multiple is 1. So that's pretty straightforward. For Ca2 plus and F negative, the least common multiple of 1 and 2 is 2. So you need them to both get to be +2 and -2. So that's kind of what we're doing, is we're looking for the least common multiple. So in this case, lithium and oxide, which we'll talk about the names in just a little while, lithium +1 and oxygen -2, when they come together, we're going to need now 2 lithiums for every 1 oxygen, because again, the least common multiple is 2. So in order to get a +2, we're going to need 2 of those. An easy way to figure this out is called the crisscross method. And the way that you can do that is you can take the charge, now not with the charge, but the number of the charge, and crisscross down to the other element. So you can see here in this example, let's look at aluminum, Al plus 3 and O negative 2. Well, if you use the least common multiple, you could say 3 and 2, you need to have 6. So in order to get a plus 6, you're going to have 2 aluminums. In order to have a negative 6, you're going to have 3 aluminums. Well, notice that if you crisscross, the 2 will come down, not the 2 from the negative 2 on the oxygen will come down and become the subscript for aluminum, and the 3 from the Al plus 3 will come down and become the subscript for the oxygen. Again, they each now will have, so if you do the least common multiple, that works too, but the crisscross method is a little bit of a quicker way to do that. So look over on the right at K plus and P negative 3. So again, the least common multiple here is 3. So we're going to need 3 Ks and 1 P. The easy way to do it is to crisscross to bring that 3 down to the other element. So the negative 3 from the phosphorus becomes the subscript for the potassium, and then the positive 1, not with the positive, but the 1 from the plus 1 becomes the subscript for the phosphorus. And generally we don't write 1. If it's just 1, we don't write it. It's assumed to be 1. The trick with the crisscross method, though, is that you do want the lowest ratio. So you know, here, if you were to take the crisscross method, if you just look at Mg plus 2 and O negative 2, you would say, oh, well, they already are equal. So MgO is the lowest ratio, 1 to 1. If you did the crisscross method, you might come up with Mg2O2, and that's fine, but always take a minute and look and see if you can reduce it down any further. So in this case, the lowest ratio is 1 to 1, MgO. So that would be your best answer. So just be a little bit careful when doing the crisscross method. Polyatomic ions, and here's where it's very helpful to be able to recognize polyatomic ions. They should stay together as a group. So here, if we have Al plus 3 and CO3 negative 2, the CO3 is one group. So if it helps you to put parentheses around it, at least at the beginning, that's fine. In this case, you do have to have parentheses in the final compound because you have 3 of them. So again, least common multiple, you should have a plus 6 and a minus 6, so you would need 2 aluminums and you need 3 carbonates. So that's, or if you do the crisscross method, you see the 3 comes down, and again, do put parentheses around it because you have 3 CO3 groups. And then the 2 comes down for the aluminum, Al2CO3 group 3. You wouldn't say group 3. You would say Al2CO3 parentheses 3 or just 3. Notice that in the next one, Na plus and PO4 negative 3. Now again, to get least common multiple, they both need to be 3. So we would have to have Na3 PO4. And this is where being able to recognize a polyatomic. I think in the one above, the CO3 with the parentheses, you can sort of see, oh yeah, that's a polyatomic. But in this one, Na3PO4, because there's no parentheses, you may get yourself a little bit confused, and you may, if you're, and so far what we're doing is crisscrossing to form the formula, but if you have to uncrisscross it to get the ions back out, you may get a little bit confused with the subscript from the polyatomic or the subscript from the crisscross method. So that 4, remember, belongs to PO4, which is the polyatomic. And that's why it's so crucial to be able to recognize them. One little hint I have is that if you see an ionic compound that has more than 2 elements, it has to have a polyatomic in there. So having your polyatomic sheet handy or memorize them will really help you down the line. Okay, if you've got 2 polyatomics, you just do the same thing. So NH4 plus and SO4 negative 2, you're going to need 2 of the NH4s to combine with 1 SO4. So NH4 parentheses 2 SO4. So do be careful with polyatomic ions and be able to recognize them.